Hi, this is an example problem on the Doppler shift from chapter 16. Pause for a moment and read the question. So for the Doppler shift, this has to do with the change in frequency that an observer detects based on relative motion between the source of the sound and the observer of the sound. Now there's a master equation that we can use here for any type of motion in which the observer and the source are moving. The most important thing here is we want to identify plus and minus signs here. It's key to remember that if you're moving towards or approaching, this always produces an upwards shift in the frequency. It becomes higher pitched. So if the observer is moving towards, we need to choose the appropriate sign, plus or minus, that will increase the frequency. If it's going to increase for the observer, it'll be a positive because the observer is in the numerator. And it's the opposite for the source. If the source is moving towards, approaching, it also needs to produce an upward shift, but because the source is in the denominator, you put a minus to make the denominator smaller, and that gives you an overall increase in the frequency here. So let's go ahead and we'll paste that equation in real quick so we can use it. And we've got two cases here. It's good to draw the cases to identify whether the objects, the observer and the source of the sound, are approaching each other or not. So in part A, they are approaching each other, so they're driving towards each other. Let me go ahead and draw this for a second. Alright, so draw a picture of the ambulance here on the left, and it's moving towards the car, which is on the right here. And, well, they're not going to collide. They're in opposite lanes. But they're approaching each other with the same speed. Let's calculate what the observer's frequency is. So this is the observer's frequency, which is Doppler shifted from the source frequency, Fs. And so in the top we have the equation for the observer, and in the bottom we have the equation for the source. And if we look at the speed of sound, that is just v in the denominator. So let's look at the observer. The observer is moving towards the source, and so that means they're going to cause the frequency to increase. So this overall thing needs to go up based on the observer. That means we're going to choose the plus sign here. And for the source, I guess I'll do it like this. Observer makes it go up. For the source is also moving towards the observer. That's going to also cause this whole term in the parentheses to increase. So that means we need to choose, since the observer is here in the denominator, we need to make that smaller in the denominator to make it increase overall. That means choose the negative sign. And now we can go ahead and calculate the value here. So the source frequency emitted by the siren is 400 hertz. And we've got the speed of the observer divided by the speed of sound, 345. I can put in the units here if we want, but these are ratios, so they do cancel, which is nice. And in the bottom, 1, it's minus the speed of the source, 35 meters per second, and again divided by the speed of sound. And when we calculate that, we get an answer of 477 hertz. So both the source and the observer moving towards each other generates an increase in the frequency, a higher pitch. Let's look at part B. Part B is going to be after they've passed each other and then they're moving away. So if we can go ahead and just take our same picture again. In this case now, this guy's moving away over there. And this guy is moving the opposite direction. So for part B, we're going to use the same equation again, but this time we need to repick the plus and minus signs here. So for part B, in this case, plus or minus, now the observer is moving away from the source. So for the observer, that is going to cause the parentheses to decrease the overall value there. So that's the contribution for the observer, moving away, receding, negative sign to reduce the frequency. The source is also moving away from the observer, and that means we're going to have to also decrease the term in the parentheses. So both the observer and the source contribute to lowering the frequency, and that means we need to make the denominator bigger in the bottom if we choose the plus sign. And from there, all we do is we put in the same values again and calculate. So all we can do is go ahead and take this, and we can go ahead and just change the plus and minus signs to be accurate because the speeds haven't changed. And we put that into the calculator, we end up with a value of 337 hertz. So in this case, both observer moving away from the source moving away from the observer, they both contribute to a reduction in the observed frequency heard by the observer. Now it's possible to have a case where one of the parties contributes to an increase in the frequency while the other party contributes to a decrease. Such an example would be, say, if the ambulance were moving to the right as it is and the observer were chasing the ambulance. In that case, the observer is trying to catch up to the ambulance. It's moving towards, it's approaching the ambulance, but the ambulance running away from the observer is moving away, receding from it. And so in that case, you'd have one contribution to increase the frequency, one contribution to decrease the frequency. And whichever one would win would be the one, basically the party that's going the fastest.